So the beginning, right? Proving this theorem, right?
Yes, sir. After equation, after in first theorem, sir.
Okay, in the first
After
theorem.
equation two.
Okay, equation two, yes, yes, yes. So equation two, I wrote IRN is like this, right?
Yes, sir.
So I also wrote that we note this del Rn dz is equal to 0 and integration del Rn dz dz equal to 0, right?
Yes, sir.
So what is its importance? So look at this part. What is it? It's a constant, right?
Yes. Yes.
So this is constant. So when you integrate, it will become 0 because integration dz here it is 0. All right.
Yes, sir.
Now this part, f prime z naught is a constant again.
Yes.
So there will be z which might be remaining. Other things are constant. So that comes to be integration z dz, right?
Yes.
Constant multiple of integration z.
Right.
So that's why this integration of this one is also. So you get this one. All right.
Okay, sir.
All right. Any other question if you have? Anybody have? Okay. So if not, let me start. So this is lecture 4. All right. So few remarks. So what we proved last time. So there are some lot of things hidden out there. So what we proved while proving. So remark 1. While proving Causes theorem for the disk, we have shown the following. The following stuff. So this part is important. If integration del r fz dz is equal to 0 for every rectangle r containing omega, then f has a primitive in omega, right? So this is very crucial remark or crucial statement which is hidden in the proof. Okay, we used that this integration is 0 for every rectangle r inside omega because of this Cauchy's theorem for the rectangle. But we used that to show f as a primitive. So in particular, we have this statement, right? We have this statement. So this kind of statement are quite important. Remark 2. Suppose, so suppose integration over a triangle, the boundary of a triangle f dz is 0 for every triangle delta inside omega, then what do you get? We get integration del r fz dz equal to 0. This is by just dividing uh, dividing the rectangle into two triangles, right? It's like this. Your rectangle, you just divide this, looking at the diagonal. So this is a triangle, and this is another triangle. All right. So what it imply? It implies something, right? Can you guess? Can you tell me what it implies?
Primitive.
Right. So that implies that if we have this integral is 0 for every triangle, delta inside omega, then also f has a primitive. Right? So in particular, hence, this implies that f has a primitive. So the statements are very important. So from remark 2, you can just recover, you can get Morera's theorem. Just by whatever I'll say, remark 3, that will actually imply. All right, third remark. So remark 3 is, let us look at Cosy integral formula in its simplest form. All right. So consider a domain. Let's say this is your domain omega. And suppose you can put a disk inside omega. So this is any disk. Let's say this is A and this is R, such that the disk centered at A, radius R, closure is contained in omega. All right. So you have this curve gamma, the boundary curve gamma. Okay. Now on that, you can use, this is a simple closed curve. So you can use Cauchy integral formula. So therefore, index will be 1 here and 0 will be in the outside. So we'll consider here. So fz by Cauchy integral formula we have fz is 1 over 2 pi I mod of w minus a is equal to r, right? This curve gamma. So gamma is nothing but this curve. So let me not go into gamma, because I can write this way: fw by w minus z dw. All right, is this fine? This is the simplest form. Where does z belong? For all z in DAR, the open disk. the open disk. Okay, so Z lies here. So Z lies here means the index is 1. Outside it will be index 0. So the whole thing will be 0. Both sides will be 0. So it will not give anything. So inside what you get is this formula. Right? Now where does W lie? W lie in the boundary, right? So W is here. So note the following. The function 1 over W minus Z is holomorphic in DAR. Right? In the open disk, this function is holomorphic. Right? Of course, holomorphic doesn't matter that much, but what is important is the following: 1 over W minus Z, one can actually write in terms of 1 over W minus A plus A minus Z, like this, right? And which is nothing but, if you take common, W minus A, it would be 1 minus Z minus A by W minus A. Now expand this and get a series which converges on DAR. Right, so this function, you look at this function in terms of Z, right? Now this way, so this way, I won't go into full details because maybe in this series course of lectures, somebody would say you that F will have a power series expansion right around the point A. By expanding this one, W minus Z, and if W its integration, so it will come out in the coefficient. So what does this mean? This means that having such formula gives you a power series expansion, and power series and the derivative of power series in Z is again, let's say, convergent power series. With the same disk of convergence. So therefore, what we proved is that in the remark 1 and 2, we already always said that F has a primitive, right? Here also says F is a primitive. So by combining remark 3, you will actually get that F will be derivative of a power series, hence a power series, hence F will be a holomorphic function, right? So combining, so from, let's say, from remark 3 itself, here remark 4. if f has a primitive in omega, then f is holomorphic in omega. So this follows by remark 3. All right, any question here? So these are few remarks, which remark 3, the full expansion you will see later on. You can do it yourself, or you will see later. All right. So that primitive actually means it's holomorphic. All right. Next, I should give you a few exercises. Since I could not send the tutorial part, so few exercises using Causes theorem. So one, compute this integral. Can you tell me what will be the value of this integral?
Two pi I.
2 pi I, yes, right, by Cauchy's integral formula. Yeah, so this is the function f. So fz by z minus 0.
But it will depend on the winding number, right? You have not given the winding number.
Oh no, I in the very beginning I mentioned whenever one writes in this form, this is the simplest closed curve.
Okay.
So exercise 2, this is compute integral mod z equal to 2 dz by z square plus 1. You have to make it in terms of partial fraction to get this. And then use winding number. Compute the following: mod z equal to r mod dz by mod z minus a whole square, where mod a is not equal to r. All right. So this is little tricky. You try. Mod z square equal to z bar. This you need to consider. Assume f is holomorphic in omega and satisfies the inequality mod fz minus 1 less than 1 in omega, then integration over gamma f prime z by fz dz is 0 for every closed curve gamma in omega. All right, we'll see an application of this one today's lecture. So this is interesting question. 5, compute integration mod z equal to 2 dz by z square minus 1. This is similar to question number 2. All right, so you'll see these are, using either winding number or Cauchy's theorem, Cauchy's integral formula. You will see more on evaluating integral while one does this complicated real integral evaluating. Finding some contour and using residue theorem, you can find certain integral, which in general it's difficult using real method. All right, let's go into today's last topic. So mostly the most general form of Cauchy's theorem. So let me first give a brief generalization of curves. So generalization of curves. So which one calls chains, right? So what is mean? A curve is a continuous function. So here, so this one is a curve. But suppose you have like this, 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 this. You want to consider all this together. Okay? How do you consider? So this gives you a chain, and this is a curve. So a curve is always a chain, but a chain is actually kind of some disjoint union of curves. Well, one can make this as two curve, and so on. Like you see here. Here, for example, you can think of this one as either one curve or four curves joining together, right? Here, of course, for to say this is a curve, you have to join together, but you can actually work without having joining together. So let me define. So this is actually, so what you try to imagine is disjoint union of certain curve, finitely many curves, and you want to integrate on them. All right. So that's where the concept of chain come from, and one can add and subtract chain. So there is this formal addition subtraction is there. So maybe let me define first. A chain is a formal finite sum of curves which by itself may not be a curve, need not be a curve actually. So we'll say, so these are a few definitions. We say two chains gamma 1 and gamma 2 are same, identical if integration over gamma 1 f equal to integration over gamma 2 f for all f continuous on gamma 1 union gamma 2. So what does this mean? So first of all, we have to define what does it mean, right? We did not define yet. So let me define that. So you have, let's look at another example. Right? Annular region. So this is one curve, gamma 1, and this is one curve, gamma 2. All right? Now this together is not a curve, but sometimes you have to integrate both of them. All right? So one can look at gamma 1 plus gamma 2. This is, let's say, gamma. This is a chain. And integration over gamma f will be defined, dz will be defined as integration over gamma 1 f dz plus integration over gamma 2 f dz. All right. So this will be the definition for all practical purpose. All right. So we just add corresponding each curve. So this curve might be goes around this way. You can call it minus gamma 2. So then this would be integration gamma 1 minus integration gamma 2. So on. Right? Is this clear, the definition?
Sir, gamma 1 plus gamma 2 itself
Yeah.
has a different definition.
So what is different definition?
There, it will be there is a map from closed and bounded interval to this path such that we can parameterize half one with gamma 1 and another half one with gamma 2 such that endpoint of gamma 1 and starting point of gamma 2 match.
It doesn't match here. These two are distinct.
Yes, yes.
So these two are distinct. So if it matches, you can actually consider it to be a single curve here for the purpose of the chain. It doesn't matter.
Okay.
Okay, for the purpose of chain, if there are two curves which has one terminal point of one matches with the initial point of the other, then you can combine these two curves and consider one curve. So I'm telling you the rules of this game, though you are not will not go much further with this. So here the following things, the following operation do not change the chain. The following operations do not change the chain. All right, one is permutation of two curves. Second thing is subdivision of a curve. So whether you consider gamma, this is gamma 1 and this is gamma 2, whether you consider gamma 2 first and then gamma 1, doesn't matter. Subdivision, if gamma 1 is there, this is suppose gamma 1, and you want to divide this into two curve and call this gamma 1 1 and gamma 1 2. So does and this is, let's say, gamma 2. So gamma 1 1 plus gamma 1 2 plus gamma 2 is same as gamma 1 plus gamma 2 as chain. Okay. Third, fusion of sub arcs to a single arc. So like this one. So you have this gamma 1 and you have this gamma 2, and you are looking at gamma 1 plus gamma 2, which you can actually think of the whole thing as a single curve, which is gamma 3. It's just gamma 3. Doesn't matter. Fourth one is re-parameterization of an arc. So in the integral it doesn't matter, hence in the chain doesn't matter. 5, the cancellation of two opposite arc. So just like if we have this one, well, not actually a line. So you could have this gamma 1, gamma 2. You have this direction, and then gamma 3, gamma 3. Well, gamma 3, let's say gamma 4, So here what we get is gamma 1 plus gamma 2 plus gamma 3 plus gamma 4 is nothing but gamma 2 plus gamma 4. All right. So this 5 does not change the chain. Next is addition of two chains. So addition of two chains is the corresponding. You add the corresponding curves. You write as plus gamma 1, gamma 2, gamma n, whatever. If there is a repetition, you actually give a multiple. So suppose like this: if gamma 1 plus gamma 2, and then plus gamma, this is one chain, and gamma 2 plus gamma 3 is a different chain, then sum will be gamma 1 plus 2 gamma 2 plus gamma 3. Right, so this the coefficient would occur as positive integer. Yeah, any question here?
Sir, is it a kind of convention or we have the proofs of all these?
Oh no, you can look at conventions. These are conventions. I mean, you can, well, it comes from definition as well. So, I mean, I'm not going to give any proof here. So these are the, once you define what is a chain, this 5, whatever I said, does not actually contribute to it doesn't change the chain that you can actually show. And this sum, well, you have this sum is nothing but this, it comes in the same direction, to same curve. So if the direction changes, it comes as minus sign. So if it comes twice, you just, it's convention. Yeah, this is convention. You put a number here. Well, if you know a little bit of algebraic topology, this would not actually, you'll not get surprised. So these things are quite familiar if you, I mean, define homology, cohomology. But I'm not going to go into this one. These are basic things, and these are generalization of the curve. Whatever for the integration, the theorems we have proved, we can actually do it right here also. So corresponding to closed curve, we have here cycles. So a chain is called a cycle if it can be represented as a sum of closed curve. So if you look at this closed curve, so for example, this annular region, this curve is called say gamma 1 and gamma 2. This gamma 1 plus gamma 2 is a cycle. All right. Now one can define the index of index or the winding number of a cycle gamma. So gamma is, let's say, gamma 1 plus gamma 2 plus gamma k is defined as a 1 over 2 pi I integration over gamma dz by z minus a. Well, it's, I mean, you see, this is the usual definition, and then you have our sum of j from 1 to k integration over gamma j dz by z minus a. So which is nothing but summation j equal to 1 to k eta gamma j comma a. All right. So this will not go much deeper. So those all the theorems which we have done for this closed curve or the curves, we can do it for chains and cycle. Okay. So
Sir, I have a doubt, sir.
yeah, sure.
Sir, if the orientation of gamma 2 is in the opposite direction,
Mm.
can we consider it as a cycle?
Oh yeah. Cycle is just I mean it should be closed curves. So if you look at this one, for example, let me draw another one. So let's say this is the same picture, but let's suppose this gamma 1 has the same thing, and here you have this direction, right?
Yes, sir.
Call it gamma 2 tilde. So this then it will be gamma 1 plus gamma 2 tilde, which will be equal to gamma 1 minus gamma 2, which is not same, right?
Yeah, it's not this, but still it is a cycle, sir.
Yeah, it is a cycle because it can be represented as sum of closed curves, formal sum.
Okay. So the orientation is not a problem,
Orientation
right?
is, or if orientation difference, curve changes. The curve
Okay,
changes.
okay.
So
Okay,
hence,
okay.
the chain become different.
Okay, sir. Thank you, sir. Thank you.
Welcome. All right. So so let me whatever in the next we'll look at is what is called homotopy and what is homologous to zero curves. So this can be done for chains and cycles also, but for the simplicity and the constraint of time, I'm not going to chains and cycles. You can think of just I mean chain as a single curve, and then we can do this. So what I want is here, suppose so homotopy between two curves. Suppose gamma 1 and gamma 2 be two curves in a topological space X. That is, gamma 1 is a continuous map from, we'll now look at the parameter region as 0, 1 instead of AB to actually combine the notion using the standard notion in algebraic topology. Continuous. One can use AB, doesn't matter actually. Gamma 2 is again continuous. We say that gamma naught or gamma 1 gamma 2, I said that, yeah, gamma 1 is homotopic to gamma 2. So in the notation, gamma 1 would be homotopic to gamma 2. This is the notation. If there exists a continuous map H stands for homotopy, 0, 1 closed interval cross 0, 1 closed interval 2x such that h of t comma 0 is, I'll give you a picture so it doesn't comma. Yeah, actually 0 1 makes more sense because it is easy to remember. Let me to consider 0 and 1 because it's 0 and 1 here. Here it is 0 and 1, it matches nicely. So call this 0 and 1. Yeah, so this is gamma 0 t. So you get when the second one will be 0, it'll get gamma 0. So here is the picture. So suppose this is gamma 0 and this is gamma 1, or maybe I would call this as gamma 1 and call this as gamma 0. All right, so ht0 is this one. ht1 is gamma 1. It is expected, right? So this is the following. Let me take a different color. So here it is like 0 to 1 and here also 0 to 1. All right, so what do you want? Then what happens to others? So here is what happens. So you can actually, for every t you have a curve in continuous fashion. You can actually reach from gamma 0 to gamma 1. Very easy to look at, right? Now you can impose certain condition. So for example, so homotopy.
Sir, sir, one
Yes,
question.
yes.
This column in middle one is not defined here.
Why
Only if t lies between 0 and 1, then it was not defined here. Only
No,
at h.
h is a continuous function, right? So
Yes,
you
sir.
fix s here. So
Yes.
fix s in 0 and 1. Let's say open 0 and 1. Open 0 and 1. So you define gamma s t is h of t comma s, right? So this is
Okay,
it.
sir. Oh, okay. Thanks.
This is it. We get a curve. Now this you might not have seen. This is very general. What you have seen is fixing endpoints. So homotopy fixing the endpoints. So the definition is same. So let me draw a picture. I'm not going to define. So here two curve. There will be this gamma 1 and maybe this will be gamma 0. Note here, the endpoints matches now. Endpoint matches now. All right. So in this case, a homotopy will be for each s you have this where the endpoint is fixed. and going gamma 0 to gamma 1. All right. So in this case, homotopy would be h would be continuous function from 0, 1 to 1 to x, such that again h of t comma 0 is gamma 0 t, h of t comma 1 is gamma 1 t, and h of here 0 comma s should be h of 1 comma s for all s in 0 1. This is fixing endpoint. So this is fixing endpoint. Right, but we will not use this fixing endpoint part. We will use this one, but for closed curves. All right. So is the definition clear? Definition of homotopy?
Yes, sir.
Okay, for example, let me give one example at least. So suppose omega is something like this. This is omega, and gamma naught is, this one is gamma naught. Okay, and gamma 1 is just a constant curve. So gamma 1 t is z naught, right? My claim is that gamma 0 is homotopic to gamma 1. So how do you give a homotopy? H from 0 1 cross 0 1 in omega. So inside omega is the topological space now. Omega. So define H, this one, you move this, the same thing, whatever is there. My drawing is not okay, like this, going smaller and smaller and getting to z naught. So let me define explicitly. HTS would be 1 minus S gamma naught T plus S Z naught. So you see here, so this is your continuous map because gamma naught is continuous and S is, it's polynomial in S. So here H, if you write T comma S equal to 0, so what you get is gamma 0 T. H of T comma 1, if you put 1 here, so this part vanishes. So what you get is Z naught, which is gamma 1, right? And that's it. That's what you want. H is continuous and having this property, right? So is this clear?
So sir, for any gamma naught and gamma 1, can we give this kind of H map?
No, it's not always true. So for example, here example 2, non-homotopic, homotopic curves. So let's consider annulus. So omega is your annulus. This is omega. Now consider a curve like this. This is a curve gamma naught, and consider another curve here. This is gamma 1. So gamma naught is not homotopic to gamma 1. Okay, why? Because by previous argument here, the previous argument, this homotopy gives you that this one is homotopic to constant. Okay? But this one actually is not homotopic to constant. You cannot shrink it.
But sir, to show these are non-homotopic, we need to prove that there will be not H kind of function, right?
You will see the proof in a moment using a winding number.
Okay.
So one will be winding number 0, other will be winding number 1. That would actually give that they are not homotopic. Okay, but just by I'm going to state the theorem. So if gamma naught and gamma 1 are two closed curves in omega such that gamma naught is homotopic to gamma 1 in omega, then for all alpha does not belong to omega, the winding number of gamma naught with respect to alpha is equal to winding number of gamma 1 with respect to alpha. Now this actually proves your concern, right? So if they are homotopic, they should have the same winding number, but one doesn't have. One have winding number 1, other is not. Right? So it's here. Okay?
The converse need not be true here.
I'm not saying converse.
No, so in general, it is difficult to say two paths are homotopic or not. Is there any if and only kind of theorem?
No, here, I mean, does this prove or not?
This will give me that these two curves are not homotopic.
That's not the thing, right?
Yes, but in general, how to check whether two curves are homotopic?
That goes into algebraic topology. So you look at Moncrief's book, you will see few things, how to show two curves homotopic to each other, which is of course a difficult thing. But here in complex plane, winding number actually gives a nice invariant. Nice invariant when winding numbers are same. Even then, whether this is homotopic or not, that is a difficult question. But winding number separates some things.
Okay.
Okay. So this converse may not be true in this case. Well, for the case of domain, it is true. But here, I mean, you can find that certain curves which are zero winding number, but still non-homotopic to 0. That I mean, you can look at Conway's book for an example. That goes into topology. Okay, so how to prove these things? So how much time we have? 30 minutes. So that is good. Okay, so let me call this theorem as 4.1. Let me state a lemma to prove, which will be used to prove this one. So the question is how to go from this homotopy to certain integral, right? That is the question. So let gamma 0 and gamma 1 be two closed curves assume there exists alpha in C such that mod gamma 1 t minus gamma naught t is less than mod alpha minus gamma naught t for all t in 0, 1. then the winding number same. So winding number of gamma naught with respect to alpha is same as winding number of gamma 1 with respect to alpha. So this might look a little bit different, but what is actually will be showing is this inequality. So let us give a proof of this lemma. Proof. So since alpha does not lie in well, what you need here is, well, these are curves in omega. Alpha does not belong to, well, here something is required, which I forgot to mention. So in this lemma, where does alpha belong? There is this alpha. So alpha should not lie in, alpha does not belong to gamma 1 and gamma 2, the trace of gamma 1 and trace of gamma 2. Otherwise, you cannot define the index or the winding number. So that part is crucial. So alpha does not belong to gamma naught and alpha does not belong to gamma 1. So define gamma from 0, 1 to C as gamma t equal to gamma 1 t minus alpha by gamma naught t minus alpha. Okay? Now what is gamma prime t by gamma t? Check that. This is nothing but gamma 1 prime t by gamma 1 t minus alpha minus gamma naught prime t by gamma naught t minus alpha. So the previous argument gives you that this integration is 0. Why? The condition. What condition I have? I have this one, right? This one. So gamma t, or let's write it 1 minus gamma t, 1 minus gamma t, which is nothing but 1 minus gamma 1 t minus alpha by gamma naught t minus alpha. So this is nothing but gamma naught t minus gamma 1 t by gamma naught t minus alpha, and this is strictly less than 1 by assumption. Right? So look at this. This one. This is strict here. So hence we can actually use the previous exercise to imply that integration gamma prime t by gamma t on 0, 1, let's say. It's on 0, 1. dt is 0. This implies index of gamma naught with respect to alpha. Winding number of gamma naught with respect to alpha is winding number of gamma 1 with respect to alpha, right? So this gives integrating this gives winding number of gamma 1. Here winding number of gamma naught. All right. So this lemma will be used to prove the theorem I mentioned, but the proof of the theorem is complicated, using a lot of topological stuff. I'll give you the geometric argument. So here is it. You have let's say you have gamma 1, this one, and you have gamma naught, or maybe let me for a little better way. Gamma naught. All right. What was the assumption in the theorem? Gamma naught and gamma 1 are two closed curves in omega, such that gamma 1 and gamma naught and gamma 1 are homotopic. Then you want this. All right. So homotopic is given. So we have actually given this homotopic. So we have certain curves going from one side to other. So on. You have a homotopy. A homotopy is given. A homotopy is given. So, which means you have this side 0, 1. You have this side also 0 and 1. So 0, 1, here also 1. And corresponding to each S, you have a curve. And curve is given in terms of the parameter t. So this side is t and this side is s. All right. Now this homotopy is given. Now what we actually need, homotopy, winding number. So you have to go through this winding number. The point is, one other thing is given, which is crucial. Alpha does not belong to omega. So let me draw omega. So this is a domain omega. So everything is there inside the domain omega. Okay. Now you have point alpha. Let's say alpha is a point here, which is outside. So it is quite far away from the curve, right? It is quite far away from the curves. All right.
Sir, why do we draw these curves gamma s between gamma 0 and gamma 1?
because it is given now. So it is this one is given. So you have a homotopy given H, right? So the point is you have given H from 0 1 to 0 1, 0 1 cross 0 1 to omega continuous, such that H of t comma 0 is gamma 0 t, and H of t comma 1 is gamma 1 t, and you have this H of 0 comma s is equal to H of 1 comma s. All are closed, right? So this actually H, and H is just a continuous, it may not be smooth. That is the point. So we need to go from one thing to other, and we have to apply this one, right? So we have to show this part, right? So this is what we are going to show. So from whole of the image of the H, this distance is, let's say, 2 epsilon. Distance is much bigger. And what you would approximate in the following way. For each curve, you would actually consider piecewise smooth curve. All right, like this. Piecewise smooth curve. Piecewise actually polygonal path. All right, you approximate this way. Similar thing here. Maybe let me take a different color. Yeah. So here, what we would like. Is it visible, this color?
Yeah, it is visible.
Okay. So you approximate this, each of the curve by small one. One can write this explicitly, but it's better. These are straight line segments. You divide the interval and each of the small partition, you define this interval, having the points inside on the curve for the endpoints of the partition. Okay, and you go on like this. Now the point is here, so this one, say gamma naught, this blue curve, let's say this is gamma naught tilde, and each of this interval, what you need is to, here this interval you divide in partition. So partition it n times. So each of this is 1 over n. Okay, you can make n to be larger to get this to be smaller, right? So this curve, let's say this is gamma 1 over n tilde. This one, the green one, and so on. That and here you get correspondingly gamma 1 tilde. All right. Now this gamma naught and gamma naught tilde are very close, right? Winding number of alpha does not matter. Again, by this lemma. By this lemma, you can show this. Gamma 1 will be gamma naught tilde, and this is gamma naught. This is very small compared to this is very small compared to this. All right. So you go to gamma naught tilde, and then from gamma naught tilde you go to gamma 1 over n tilde, and so on in continuous fashion. And each step, and make n large so that you can actually you can keep on satisfy the property this one at each step. All right, at each step you need to satisfy this property, and from gamma naught go to gamma 1 tilde, and so that this winding numbers of gamma 1 over n tilde with respect to alpha is same as gamma naught tilde with respect to alpha, and go on. And this way you can move out until gamma 1 tilde. And again, gamma 1 tilde will be very close to, it is the approximation with polygonal path. Sorry, what happened? Polygonal path. Yeah. Of gamma 1. So hence this gamma 1 tilde, winding number of gamma 1 tilde will be same as winding number gamma 1. So this homotopy actually allows one to pass from gamma naught to gamma 1 in continuous fashion, so that at each stage you keep on satisfy this property, and that remains this winding number would be same. All right, does this pictorial thing is, the idea is clear? I didn't write the proof. You can look at Rodin's book if you want a detailed proof. I don't have time. Yeah, is this pictorial idea is clear? Okay, so next is the Causes theorem. So before going to few definitions I need to give. So first thing, a curve gamma is said to be homotopic to constant or null homotopic if gamma is homotopic to, well, this is called, this is the notation, gamma is homotopic to 0 if gamma is homotopic to a constant curve. Another definition, let gamma be closed curve. Any question? Let gamma be a closed curve in omega in a domain, in a not domain, in an open set omega C. Gamma is said to be homologous to 0, which means gamma is right this way. If winding number of gamma with respect to any point A will be 0 for all A in C minus omega. For every point omega, for every point A outside omega. Is this two definition clear? Yeah. One is homotopic to constant map. I will give an example, right? Like this one. homotopic to a constant. This one, this example. And homologous to 0, it's defined in terms of winding number. Okay, so what we proved in the theorem is that we proved that if gamma is homotopic to 0, then gamma is homologous to 0. So homotopic to 0 in omega, this is in omega. Okay, the previous theorem says this. Now, next theorem. Causes theorem. Let f be holomorphic on omega, then integration over gamma f dz is 0 for every closed curve gamma which is homologous to 0 in omega. Well, again, we need, since because of time constraint, we need to give a pictorial argument. So this argument is very nice, actually. So look at this carefully. So firstly, let me draw an omega and a curve inside. So this is gamma. So next thing what one would do is put a net of squares. Put a net of squares on this. By the way, note that if we prove this statement, we can prove that if gamma is homotopic to 0, then also integration is 0, right? Because of the previous this remark. All right. So this is what we need to prove, actually, to prove the homotopy version of Causy's theorem. So first thing is, as I said, put a net of squares. All right. Next is you actually get the, what should I say? Oh well, yeah, this is fine. So we considered first we consider omega to be a bounded domain. Omega can be unbounded as well. So we'll argue that later. So next is we will actually now look at the squares that completely lie in omega. Okay. So it is something like this. So look at this one. In fact, one could just look at near the curve, something like this, 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 this. Oh, you should not touch. So this, 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 like this. Yeah. So containing the curve gamma, and which lies inside omega. Right. So consider all this rectangle. So one can do this. This is actually having finitely many squares. So each of them you can actually call this something like this Qj. So this is the rectangle Qj. J belongs to J. So choose what should I say? So length of the grid small, length of this one, choose, this is delta. So choose delta small enough, small enough such that this set J is the index set, J is not empty. So J is collection of J such that Qj contains in fully omega, actually such that one of its side intersects, oh well, does not intersect. Oh, I didn't intersect gamma. Or the smallest set of rectangles such that gamma lies, actually this gamma lies union of Qj, J from 1 to J, 1 to J is in J, capital J. All right. Okay, this is fine. Now you call this domain, this whole domain, the interior of this one, as omega delta. So omega delta is by definition interior of union Qj, J belongs to J. Okay, so you see here we have chosen in type of gamma. So if gamma can be in fact bigger near the boundary, so basically you can actually have to consider for all Qj lies in omega entirely. That you have to consider. Here, depending on gamma, we have considered this way, but actually what we should have done is the following. We should have done something like this, whatever. Yeah, this, the whole thing, this, and then coming from here, the biggest one. like this, like this, like this. Yeah. So in the biggest one, you can make delta small so that all the curve will lie there. Whatever curve you choose will mostly lie. Depending on delta, you can find such way. That part is important. Okay. So now you actually choose a zeta here. Choose a point zeta in omega minus omega delta, somewhere here. Call this zeta. And you consider another point in, let's say here. Let's say zeta naught. Something like this. So, and consider this line segment. So omega delta, so call this L naught. So we have L naught intersection, omega delta is empty. So omega delta is inside, that side. So this one gives you, so this L naught intersection omega delta is empty, and this actually gives you eta of gamma zeta equal to eta gamma zeta naught, because we have proved last time that line segment does not intersect gamma, so it will have the both endpoint will have the same index with respect, same winding number with respect to gamma. So remember the last time we proved this. So in particular, actually we can actually this would imply we can get the gamma with respect to zeta, the winding number is 0 for all zeta in the boundary of omega delta. So in the yellow boundary, you can have the same thing. All right. Now this is it. This is enough topological stuff. Now we actually go into the integral formula. So suppose Z belongs to so interior of some q j naught. Let's say j naught lies in J, capital J. So then 1 over 2 pi I by the integral formula, Causy's integral formula, del q j f zeta by zeta minus z d zeta will be fz if j naught is equal to, or j equal to j naught. J equal to j naught. Else it will be 0. Okay, so and you can actually from here you get that fz is equal to 1 over 2 pi I, considering all the rectangles, union of all the boundaries of the rectangles, and cancelling the sides which passes twice. So boundary of omega delta f zeta by zeta minus z d zeta for all z in omega delta. All right. So this holds. Is this clear? Well, I have crossed the limit, this time limit, but I'll need 3-4 minutes. Is it fine?
Yeah, please.
Yeah. So once we have this one, then we just integrate over gamma, both side, is equal to integration over gamma 1 over 2 pi I integration del omega delta f zeta by zeta minus z d zeta and then dz. Now, since all these functions are continuous over gamma as well as gamma delta, so this one can interchange the integral. So interchanging the integral, order of the integral, what we get is integration over del gamma omega delta 1 over 2 pi I integral over gamma d zeta by zeta minus z f zeta. Sorry, dz here. Dz f zeta d zeta. Now what is it? This one?
Winding number.
Winding number of zeta. And what we did here? 0. So zeta lies in the boundary of del Lilly. See, it falls down properly. So this is 0. So if the next case, if omega is unbounded, so we consider r greater than 0 big enough such that the gamma, the trace of gamma lies in omega intersection d 0 r. Yeah. And then the above argument follows. All right. So what I mentioned just before going into the proof of this theorem, which is theorem 4.4, Causes Theorem, homotopy version. If gamma is a closed curve in omega such that gamma is homotopic to 0 in omega and f is holomorphic in omega, then integration omega or integration over gamma fz dz is 0, right? So homotopic to 0 would imply this is homologous to 0 and hence previous theorem will get it. And next remark or maybe definition, a domain omega is called simply connected if any closed curve in gamma in omega is homotopic to constant. So which means it is gamma is homotopic to 0 for every closed curve. So for example, disk DAR simply connected. So here in this case, then the Causes theorem would come if omega is simple connected and f is holomorphic in omega, then integration over gamma f dz is 0 for every closed curve. And note here, this is actually if and only if statement, right? We have shown this is true for rectangle implies that f has a primitive. In turn, if this f becomes holomorphic. So this is actually simply connected if and only if integration 0. So the theorem is if and only if all f holomorphic in omega and for every closed curve gamma in omega. All right. So and you look at this annular region. Here, this is not simply connected. So this is where if your omega is this is not simply connected, as this curve is not null homotopic. And so this is doubly connected or multiply connected to omega. Okay, which has the comp. So if C minus, so omega is simply connected. So you can deduce what we proved till now. If and only if C infinity. Here you will need to look at C infinity minus omega is connected. Well, if you there are a lot of characterization of simply connectedness. This one. So when it is not simply connected, domain is called multiply connected. Okay, so I have taken already around 10 minutes. Yes. Thank you. So I'll stop here. If you have any question, please.
Sir?
Yes.
Sir, how we prove that holomorphic functions are analytic functions?
Oh, that's in the very beginning, right? So path series are analytic function, right?
Yes, sir.
So we showed in the remark. So you will see in the details, like maybe in some lectures. So here, let me go back to the remark 3. Yeah. So here, in the remark 3, so what we proved, holomorphic implies you have Cosy integral formula, right?
Yes.
So once you have Cosy integral formula, then you can have actually power series expansion using this one. See, this is 1 minus z, right? You can expand it, right? This you can expand it, right? 1 over w minus a times sum over n z minus a power n by w minus a power n, right?
Yes, sir.
Now you incorporate this one in the integration here. And then you change the summation and integration. So you get a power series. Well, the convergence part, I leave it to you, but it converges. Okay, so that's how you show that once you have this integral formula, you can have a power series using this one. Hence, it is analytic, right?
Yes. Yes.
Okay.
And the convergence is straightforward, sir.
Analytic, yeah, power series. You take derivative with respect to z bar, right? Term by term power series. I mean, if you have power series, you take the derivative inside the same summation, right? So you have to give the argument that you can take the derivative inside the summation. So that part comes from real analysis actually. Taking derivative inside the summation. And now with respect to z bar, you take derivative, each of the term will be 0. So hence Cauchy Riemann equation satisfies. Right? So is this clear?
Yes.
Okay. Yeah, any other question?
Sir, if
Yes.
suppose there are two curves,
Yeah.
and if the initial point of one curve is the terminal point of another curve, then it is a chain, right, sir?
Oh no, chain is any actually the disjoint curves also will be a chain.
Okay.
So
And,
you
no,
do not need. So you are considering this one, right?
Yes, sir.
But you don't need this. Just any union. So those
Okay.
whatever integrals we have done for curves, one can generalize to chains and cycles. So this Cauchy's theorem are true for chains and cycles actually. So one can define homologous cycles, and you can
Actually, the question was different, sir. Actually, I misspelled something. So actually, I'm asking. Suppose two curve is there. So the terminal point of one is the initial point of the other. Then it is a curve. Huh?
Yeah, it is a curve.
Suppose it intersects in between. So is it again a curve?
Yeah. Curve is anything. So it's not simple. So this can be a curve, right? This is a curve. So here, so this we consider as curve. So these things can happen. We have considered all this. So these are included in our defining winding number and all this. They can intersect, they can move around, right? Twice, thrice, right? Intersection is the whole curve. The self-intersection is in the whole curve, right? So if you move in the circle twice, for example, like this. So it's basically a lot of intersections are there. These are curves. Once you can parameterize continuously, and of course we need piecewise smooth for our purpose, from an interval AB to C, that's a curve. Yeah, any other question?
Sir?
Yes.
Sir, for a disk, we have a Cauchy integral formula, and for multi-connected domain, so the same formula works, or say, is there anything other? I mean,
so formula is basically the same, right? So you need the curve. We have done it for curve with some certain winding number, right? So we now have this one, right? So we have proved for any curve homotopic here, you get 0, right? So in this case, you can actually, whatever I proved here, where did I prove it? Here. Yeah, so this theorem is true for chains, for cycles also. Okay, so this theorem is true for cycles homologous to 0. So that is just union of certain closed curve, right? Each of them has actually the winding number 0. Or the sum actually would have winding number 0. So this one would also work. So you can go through the proof, and then that would actually imply one can have formula for, let's say, this annular type region. So suppose you have this two curve, one is this, another is this, like this. So you can actually have, yeah, the Cauchy integral formula. So Cauchy integral formula follows from Causes theorem. So for this kind of curve, for multi-connected domain. So these are two curves, right? So I mean, if you look at curve, then it is always true, because for curves we have Cauchy theorem, right? Now in this case it is not curve, but it is cycle. Even you can do this Cauchy integral formula here, and that's how actually you use when you develop Laura series expansion. Okay.
Yeah, okay, sir.
Yeah, actually, I mean, you don't need to go to chain for that one. One can actually make it a curve going this way and going that way, and do a this curve will be homotopic to 0. Hence, you have Cauchy theorem, and hence you have Cauchy integral formula. So this is how one can actually work without going into chains. That's why in the first course nobody talks about chains and cycles. Okay.
So are there any questions? If there are no questions, let us thank Professor Sushil Gorai for a very interesting talk, and lot of geometry he has given. And I'm sure that many participants have enjoyed the talk. Thank you, Professor Sushil. You have spent your valuable time.
Thank you.